All right. So, let me mark that down. So let me begin with a verse of scripture. This is Romans 5:8. But God demonstrates his own love for us in that while we were yet sinners, Christ died for us. So I'm trying to start all my classes with this verse. And so I think it's a good verse to remember. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you just bless this class, help us to glorify you what we do, and just have a good semester this semester. Lord, in your name I pray, Lord Jesus. Amen. So I know you guys are excited about the snow, as am I. But not as excited as my children, of course. Anyway, so there may be like a whole inch, right? Maybe 2, I don't know. Your guess is as good as mine. So this is my schedule. Let me just talk about that for a minute here. And so I have office hours. So I'm teaching applied linear in the morning, and then Calc 1. And then after that, I have a office hour in the game room in the Mountain View with the pool tables and the ping pong, so you can find me there. Those are 2 of my office hours. And then also, but you can ask me questions, but you'll probably need to bring your book and stuff because I won't have mine. But joking aside, you can actually come ask me questions there if you do so desire. Yeah. Then I also have an office hour, a more serious office hour, from 3 till 4 Monday and Friday. It's in my office, which is, if you're wondering where that is, you just go to the door, the back of the classroom, take a left, go all the way to the end of the hallway where the interdisciplinary suite is, and I'm in there. I've been exiled from... I don't think I touched the umbilicus that time. Whoa. Is it like static or something? Anyway, so fortunately I don't usually use this projector much, so whatever. Oh, every time. Anyway, so 4382M is my office number. Exciting, but there it is. I also have office hours Tuesday, Thursday from 11 till 2, and those are actually in my office. So any questions about that? All right, this is my own personal website, supermath.info. Of course, these office hours are also reflected in the official syllabus, although the fact that the game room hours are in the game room is not reflected in the official syllabus as to hide it from the prying eyes of the dean. No, I'm just kidding. He probably doesn't care. But I don't want to find out. Let's see here. So then, where are we? Oh, yes, University Physics 1. I have as you can see here, and there's also a link to this in Canvas, of course, which is a playlist on YouTube. As of now, there are, of course, no videos in here, as I'm not able to post videos that haven't been taken yet. That's called causality. It's part of physics. There you go. There's your first physics lesson. No time travel. There's also no multiverse, just while we're at it. Sorry. It's bad storytelling. It's even worse physics, in my view. But anyway, whatever. Okay, I digress. And then here's the course website. And in this course website, I have oodles of things. I have these quote-unquote lectures. These are old handwritten PDFs that I kind of loosely follow sometimes, but not so much. I will look at those sometimes just to give myself ideas when I'm lecturing. And but I also have linked here the course planner, which you should understand is essentially the syllabus, except in a more oh man, I didn't link that yet. Well, it is posted in your, what's it called? Canvas. I posted the course planner in Canvas. It is this thing here. So the course planner has the day by day, like today I'm talking about vectors, believe it or not. And then Wednesday I'm talking about vectors, and then Friday I'm talking about vectors. So vectors, vectors, vectors. And the truth is every day is vector day in here. That it doesn't stop. So don't expect it if I can just hold my nose and tilt my head or something, it'll go away eventually. No, it never goes away. So learn them. All right, so this is the day by day, like test 1 is February 7th. And seriously? And then mission 1 is due start a class on February 5th. Mission 1 is like a fair amount of work, and it's reflective of all the material that's covered on test 1. So you'll need to spend some time on that. Mission 1, yep. Yeah, go ahead. So what is mission 1? That's a good question. I will come back to it. There's also mission 2, which is right before. Seriously? Well, this is fun. All right. So there's also mission 2, which is right before test 2. And then there's, of course, the ever popular spring break, Easter, assessment day, no one cares about. And then there's mission 3, which is right before test 3, and then that's it. So there's basically 3 major missions in this class. What are they? They are lists of homework problems that I provide in PDF format. You print them out, you write the solutions handwritten on those printouts, and you turn them in class. All right? So they're submitted here in person on a printout. Have you guys had like 2 cups of coffee this semester yet? That's how much it costs to print them out. So go print them out. Yes?
Can you submit them all at once on the mission 1, mission 2, mission 3 day?
Yes, they're all due on that day. Yeah. I will open one up in just a second here. And then, so after test 3, I do fun stuff like special relativity, general relativity, cosmology, modern physics, some things like that. And here's mission 1. Here's actually what it is, all right? So like, let me scroll back up to the start of it. So in each mission, I have laid out which chapters in my lecture notes you should look at, and which lectures, like the old lectures, the ones I just showed you posted on the website, those ones. Those are the lectures in part B are handwritten. Those are the ones I was teaching out of, like last year, for example. And then, of course, chapters 1, 2, 3, and 4 of Young and Friedman, which I forgot to bring a copy of today. However, you don't really need to buy a physical copy because there's an ebook of the global edition available under the My Mastering, which you need to get anyway, because there's also My Mastering homework that you need to do, which is worth significantly less. But you know, you should do it. There tend to be more basic problems. The missions tend to be a little bit more complicated. So some things are covered in the Mastering Physics, some things are covered in the missions. Neither is comprehensive, all right? You need to do both to gain the full understanding of the material in here. But just getting back to mission 1, like problem 1, you know, here's a vector. I give you, you know, the x and y components, and I ask you to find, what do I ask you to find? The standard angle for the thing, whatever that is, right? And then like problem 2 is another question about adding vectors. Problem 3 is a question about dot products, cross products, the angle between vectors, and so forth and so on. All right, you get the idea. Well, you shouldn't get the idea yet. This is the course that you're going to learn about. But the point is, it's a PDF. It's 20 pages long, and you need to work it out. But that is it. Besides the Mastering Physics, that's the homework that's due for test 1. All right, so you should start working on that and work on it as we go. I don't have the homework divided up into little bites for every homework, for every class. I don't think your children, I think you can budget your time wisely over a period of weeks and do your best over a period of weeks. I'm not like forcing you to do homework each week. Like, you have a schedule, you have other time demands, so work it out, all right? Yeah.
What does the 50 plus 5 points?
Oh, that means there's 5 bonus points, but it's 50 points, like the, great question. Very good question, if I could find my way back to the planner. So like the long and short of it, there we go. Long and short of it is we have 3 tests. They're each worth 150 points, all right? And the missions are worth 150 points, meaning that there's 3 missions. They're each worth 50 points, but I have 5 bonus points on each. So like if you do everything and get everything right, then you've got like 15 points bonus for the course. So like suppose you miss 15 points on test 1. Well, if you did all your homework perfectly, you'd get that 15 points back, you know, so it gives you a little bit of a buffer. Mastering Physics is worth 50 points overall, and it's divided up oddly. I think I've got like 17.5 points for the first one and 17.5 for the second one, like 25 for the third one. So it's not quite symmetrical. They're a little bit weirdly divided up. And there's 10 points bonus built into the Mastering Physics. So that's a total of 25 points bonus that I've already allocated in the homework for this class just from the start, all right? So yeah. Labs, everyone needs to be in a lab section. I haven't checked to make sure that's actually happened. I hope it did. Because if you're taking this course without a lab, that means the highest score that you can make in here is a B. That's not awesome, right? You're supposed to be in a lab section. If you're not in a lab section, you need to get in a lab section. If you're not in a lab section, I wonder how you registered for it, because I thought we had it like automatically set up, but I haven't checked on it. So, everybody in a lab section? Anybody not in a lab section? Okay, good, good. Lab is like super exciting and like stuff, so I'll let those people talk to you about it. But I think those 150 points you should earn, right? At least I know when I have floated the idea, well, we should make the lab separate from the course for like Physics 201. Dr. Dinsmore's like, oh, no. Then like 30 or 40% of the students won't pass. So it's like, the lab is important. It boosts the grade overall, right? Because it's not a test and time pressure and all that jazz. The final's worth 200 points. It's comprehensive. You know the drill. I think. Let's see here. Any other thing I can tell you? If you do not, and inexplicably, but inevitably, inexorably, there are students who, for reasons I don't understand, do not bother to do their homework. And so I am just going to take your next test grade, divide by 3, and give that to you for homework. Great if you do that. So I'm not taking them late. You turn it in when you turn it in, or you don't turn it in. So, I have posted all of the homework for you day 1, so you can do it. There really is no excuse to not do that. Yeah.
What if your test grade divided by 3 is better than your homework grade? You still do that?
Nope. No. I'm not doing that. No. No. I don't want any part in that. No. That sounds like a pain. That violates a more base principle, which is I'm trying to be lazy. So, but anyway. Yes.
So is the only book we need just that ebook?
Yeah, I think it's good for you to have a physical copy of Young and Friedman, just for the sake of you reference. And he has nice pictures and facts and figures in there that you, of course, couldn't easily find on Google. But it is a good book, joking aside. And you can get an old edition of it for pretty cheap. Like I bought the global edition for myself, I think for like $20 or something. But I certainly don't think you need to buy the one in the bookstore that's like super expensive and stuff. At least not for my section anyway. What did I write? You're allowed one 3-inch by 5-inch card with writing on 2 sides for test 1, 2, 3 in the final. Oh, well, that's no fun. So I guess I let you have a 3 by 5-inch card with formulas on it for the test. I guess I wrote that there. I can't undo it, right? So yeah. Other questions? Yeah.
Do you think physics textbooks have changed significantly over the past 30 years?
Not really. I'm partial to the 9th edition of Young and Friedman because that's what I used when I was like in Physics 2 or something in 1998. So, which I think is probably before you were born. It's very likely, right? But let's see, anything else? I am here to help. I do have a fair number of office hours. You are welcome to come ask me questions in office hours about problems you have already attempted. What is not okay is to come to my office hours to work problems. You must not do this, all right? You work problems before, you find questions, you come ask me questions. I do not prefer for students to come to my office and just sit there and work problems. That's not what my office is for. So, all right. I think that's pretty much it. This is the other thing I should talk about. I am writing this thing for you guys. This is my new and improved set of lecture notes. This is like, a revision of those handwritten ones to one sort of hopefully coherent narrative. And I will be more or less teaching from the ideas in my notes, all right? So like I don't really follow Young and Friedman so much as I follow these. So I do hope you read them. Of course, I also hope you enjoy my art. starting with the cover art. I'm disappointed it kind of, come on, cut it off, because there's like a full guy like sticking out the top of the Lamborghini, which is not really like possible. I don't think that's actually how that works. So I don't know. I love these AI image generators. They're great, aren't they? Let's see here. So so like today, I'm hopefully talking about distance and vectors and such. And I do have these notes. You can read along and look in here, and it will explain some notation. For example, just here's for example, in my notes I use x hat and y hat for the vectors 1, 0, and 0, 1. Like in the textbook, it would use I hat and j hat, or just bold I faced and bold j faced. How do you write bold I and j in your pencil written work or pen written work? I mean, maybe you can. But that's why typically professors who care make you write a hat over it, because you can't write boldface, right? So I prefer X hat and Y hat as opposed to I hat and J hat. So that's just one difference that you might notice. And I also tend to not use the hat notation as much as I use the angle bracket notation, because it's just faster and easier to write. But anyway, so my notations are all in these notes. You should read the notes. You should study the notes. I would say don't stop there. I mean, it's good to read Young and Friedman in places, but anyway, get out of here. So I'm also proud of this one. I'm kind of proud of this. It's pretty nice, right? I mean, I think it took me a while. It took me a while to get Bing to do this. It took me a while, but I was happy with the result. All right, let's see what else can I show you. Batman on a helicopter. There's a cat throwing a mouse out of an air balloon. Some old handwritten stuff. Let's see what else I got. Stuff I stole from Wikipedia. What do we got? Oh, wait. Yeah? Let's see here. Another cat. Cat on this rocket sled. We'll get to all of these eventually. I'm kind of proud of this one. Got Ron Swanson and some rocket boots. There, it's a good problem. I like that problem. And on occasion, there's things in these notes which are a little bit beyond the class, like this page. Here is the transformation rule for acceleration. Like, this is probably not something that I would test on in here, or even really expect you fully understand and read. But for those of you who are interested in slightly deeper things, there are some things here and there like that. Okay, anyway. But the larger story here that I was getting to is that this is unfinished. So I've got basically up to about a day or two after test 1 the notes written for, and I'll have to be adding to this as we go on. So just to let you know where I am on that. Hopefully I'll find time to do it, but if I don't, my apologies, but I'm trying. So anyway, any questions? All right, let me put this away then, because it's kind of bothering me. So let's get into it then. So let's talk a little bit about units. So as a general point of order in here, I'm sometimes okay with you not putting units on things in the midst of calculations. I'll do that myself. So if I didn't allow you to do it, it would be somewhat hypocritical on my part. We do this all the time in math, right? In math, we just work problems where we've got no units on anything, right? However, in here, in the finished product, on the answer, it is almost never the case that you shouldn't write units. All right, so that's just one point of order. Barring some like kind of math style questions we ask here and there on occasion, for the most part, there needs to be units on answers, even if there's not units on calculations. Now, that said, it's probably a better habit to get into to put units on calculations as well in here, at least until you're confident you know how to. Once you're really, really confident about it, like skipping it, maybe is okay. But this has gotten people into trouble, right? Like, I think a somewhat famous one is like when they put the Hubble telescope up, somebody didn't do a unit conversion right, and it like ruined it for a couple of years. That was like $1 million unit mistake. These kinds of things happen. But here, just to give you an example, suppose we want to convert miles per hour to meters per second, right? So this M is for meters, S is for second. Of course, we also use M for mass. I'm sorry. It is what it is. Context matters. All right, so some important numbers to know about. A mile is equal to 5,280 feet, because we're talking about that kind of mile, not the nautical mile. All right, so 5,280 feet. And another conversion that's useful, I suppose, is that a meter is equal to 3.281 feet, right? And let's see, what else do we know? What's an hour? It's 60 minutes, right? Okay, so let's pick a specific thing just to be more interesting than just miles per hour. Let's convert 60 miles per hour, for example. Let's convert that to meters per second. So I'm going to write it out here. Miles per hour actually is miles over hour, right? So I have 60 times mile over hour. And how do I do a unit conversion in here? Oh, yeah, I think I forgot to say, I try to videotape each class, and then I post it afterwards, guys. So, like, if you're ever sick, don't come. You can just watch the video. It's cool. I don't really take points off if you're not here. Of course, you should be here, generally speaking. Otherwise, you're just making work for yourself. But if you know, I think I used the example earlier, if you have to go to, like, a wedding for a cousin in Montana or something, by all means, go. That's punishment enough. Let's see here. So, so miles per hour, and then I multiply by 1, right? So I want to get rid of hours. So like, I can do an hour is equal to 60 minutes. So I do this, right? But I'm not after minutes, right? I'm after seconds, right? So I need to convert the minutes to seconds. So I multiply that by 1 minute over 60 seconds, right? So the things I'm multiplying in blue, these are equal to the number 1, right? So that's why they're like, you can multiply by the number 1 and not change the quantity. That's what we're doing. And then what? I also want to get rid of what? Miles. So what else do I need? 5,280 feet is 1 mile. Now that's going to cancel the miles. Now I have feet. But I'm interested in what? I'm interested in meters. So I still need to multiply by what? My 3.1 meter and 3.281 feet. Now this is a good example of a place where I really would want you to write units. Okay? This is a place where writing units is kind of the whole point. So you definitely want to write units here. Now, so what happens? Hours cancel, right? Minutes cancel. The feet cancel. The miles cancels. And what are you left with? This meter and this second, right? And how does that work out?
26.82.
You say 106? Wait, what? 26.821. Let me see. I'm gonna check you on it. I believe you, but just gotta check. So I get 316,800 for the top, and then I divide by 60 times 60, which I think is 3,600, and then I divide by 3.281. You said 26.821091113 meters per second would be a ridiculous thing to write, right? So as a point of order in here, guys, I am not a chemistry professor, so I don't actually care about significant figures. They care a lot. I don't. I'm like physics. Physics is enough trouble. It's enough trouble. we don't need to add the sig fig monkey on your back as well. So like for here, I know this is kind of, you know, it might be offensive to some chemistry professors, but for us, we're just going to say this is 26.82 meters per second. And so as a general point of order, we're going to try to keep 4 digits for our answers. All right? So I'd like answers with 4 numbers in them. Unless, of course, it's something with like, you know, we also need to use scientific notation, right? Like if your answer happened to be, you know, 3,243,532 kilometers, and you wanted to write that as meters, right? Well, then I would say that that's, you know, like 3.244, if I'm going to stick with my 4 numbers thing here, times 10 to the, what? 1, 2, 3, 4, 5, 6, 6 kilometers, right? But what's this K mean? 10 to the third. Now here's something, so like, you guys asked me about, does the book matter? Well, the book matters because the book has much, you should get the book to look at. The book has much more about like multipliers and things like that. My notes currently don't have that kind of thing in it, right? It's just focused on like the more moderate to hard part of the physics. It's not so much about unit conversion and these sorts of things. That's much more covered by your textbook. So it would be good to read those things there. But K is for kilo, it's for 10 to the third, right? So if I have 10 to the third times 10 to the sixth, what do I get? I get 3.244 times 10 to the ninth meters, right? And so there you go. Like this would be a distance written in the so-called scientific notation, right? I would kindly ask that you write it in this format. Like if your calculator gives you EE9, I don't want to see it. That's not a legitimate answer, even if it's what your calculator told you. You need to interpret that in terms of the multiplication by 10 to the power, all right? So anyway, I think that's enough about this. Let's move on. Distance. So what's the distance from a point P to a point Q? It's the square root of Q, let's say Q, Q1 minus P1 squared plus Q2 minus P2 squared plus Q3 minus P3 squared. This is the distance between 2 points. So here I'm saying P is the point P1, P2, P3, and Q is the point Q1, Q2, Q3. And I'm assuming that the idea of talking about a point as an ordered triple is something you guys can understand. What do I mean by that, though? What is an ordered triple?
That'd be like XYZ.
Like XYZ, right? Yeah, think about this as XYZ. We could certainly do that. Now, all right, so let me be more specific for the sake of discussion. Let's suppose, for the sake of discussion, that it looks something like this. I guess I should think about over there, maybe. Yeah, my bad. So think about that corner over there being the z-axis, the front lower corner of the wall being the y-axis, and then the x-axis would be like sort of this black strip on the bottom of the wall. You guys see that? I'm talking about the molding strip. That essentially is the y-axis. This up here would be the, this would be the y-axis. That would be the x-axis. And then if I could draw in the corner here, I guess I probably shouldn't, but if I was to draw in the corner, this is the z-axis, all right? So how do you figure out the coordinates of something? Well, you know how much you have to go along each axis, and then you make a perpendicular, you know, step to get to where you're going. So let's just take a specific example. What was your name? Kirk. Did I get that right? Yep. Okay, so Kirk, I'm going to use a very scientific system of measurement. It's called steps. So one, ooh, I can't count. I'm going to take larger steps. 1, 2, 3, 4, 5. Basically, you're 6 steps in that direction, right? And then 1, 2, 3 this way, all right? So 6 steps in the what? He's got 6 steps this way and 3 steps that way, right? So if we were just to talk about, your foot, the coordinates for your foot in terms of steps would be something like 6, 3, 0, right? And then let's see here. Suppose then I want to calculate the distance from your foot to, what's your name? Cole. Cole's head. So I judge, I'm gonna say here, I'm just guessing, like going from where you are, 1, 2, 3, 4, 5, 5 steps this way, right? So if we're 5 more steps over, what's your x coordinate for Cole? Your x coordinate would be what? 6 plus 5, 11, right? What's the y coordinate for you? Did I do that right? Oh no, my bad. That was the y coordinate. I can't keep track of my coordinates. I obviously have not played enough Minecraft. Let's see here. So you guys know coordinates from Minecraft, right? I mean, joking aside, like, isn't that true? Or other games where you use coordinates to call in airstrikes and junk. 1, I'm just guessing, 2, 3, 4, 5, 6, 7, 8, 9. Apparently 9 in this direction. So 9 steps. I have used lasers for this before, but it occurs to me steps are easier because you always have your feet. So you're 9 in the x direction, right? And this is trickier. I need to focus the chakra on the energy on my feet in order to walk vertically. But I've seen cartoons where it's done, so it can be done, right? But it's a skill. But I think, I'm just guessing, I have to sort of visualize it, but I'm going to say 3 steps to the top of your head, since you're sitting down. So 3 steps. All right, so what's the distance from Kirk? Is it Kirk or Kurt? Kirk or Kurt? Kirk. K-I-R-K. So Kirk's feet. Distance from Kirk's feet to Cole's head. What's the distance between those, right? So, in other words, what's this distance right here? So we can figure that out. What is it? Square root of, I'm going to do 9 minus 6 squared plus 11 minus 3 squared plus, 3 minus 0 squared, right? And that's how we calculate distance in 3 dimensions. Now this answer is in terms of what? Steps, right? So we got answer squared plus, oh my bad, let me do this again here. So 9 plus 64 plus 9 equals, all right, so I'm trying to be consistent in the sense that I don't want this as an answer in here, guys, right? Like, that's not a good answer. This is physics, so we'd like to give our answer in like a decimal form. So let's see here. What is that? Now, if this was a calculus class I was teaching, that would be the answer, and if you wrote down what I'm about to write, I'd take off points. So I understand that's a little bit hypocritical on my part, but here we are. So this is 9.055 steps. So I do want, like, on the answer, I'd like to have the units, okay? But in the calculations, you could skip in this kind of thing. Does that make sense? So anyway. So I'm trying not to burden you with writing units everywhere necessarily, but I also don't want to, like, completely tell you not to do it, because there are places where not doing it will get you into trouble, especially if some evil professor gives you like a mixture of centimeters and meters, and you got to work, see where they have to cancel out, things like that. Yeah. So wait, are we good? All right. So let's talk about vectors. It's about time, right? Phew, I still have time. We go till 3:15, right? Those of you who've had my class before, you know this joke. You're not fazed by it. Let's see here. I guess this was example 1, wasn't it? I mean, that was example 1. That was example 2. This would have been example 3. And now we're to example 4. Well, it's not exactly example. Now we're to vectors. So let me talk about what is a vector. So a vector is a directed line segment. All right? So let's talk about two-dimensional vectors to start with. So in the plane, we would have something like this. A is equal to ax, ay. This is a vector. Now, so I can draw a picture, all right? And maybe it looks like this, right? So I can break that vector into 2 pieces. I can break it into its x component and its y component. All right, so let me do that. So down here, we have ax, x hat. And then going vertically, we have ay, y hat. Now, I guess I should, let me try to further explain what's going on here. When we have a vector, which is a directed line segment, we can add 2 vectors together by doing what's called a tip-to-tail sum. So like I do the red vector plus the green vector, it gives me the blue vector. So I can write a 2-dimensional vector as a sum of a horizontal vector and a vertical vector in this way. Let me explain further the math here. So this, you see, we can rewrite as ax 0 plus 0 ay. All right? And then the way scalar multiplication works is you can pull a number out. So I can pull ax out, and I get 1, 0 here. And I can pull a number ay out there, and I get 0, 1 here. This is the algebra. The picture is the geometry. There's a synthesis here between algebra and geometry, right? This is algebraic geometry. Well, it's not algebraic geometry. That's something else. We don't have a course in that. That'd be hard. All right, so anyway, the 1, 0 is x hat. This is x hat. The 0, 1 is y hat. So any 2-dimensional vector can be written as a sum of its x vector component and its y vector component, all right? Yeah.
Can you just explain the notation? Because I know the a vector symbol, but I'm not exactly sure when you're writing the x hat.
X hat is just literally this vector, 1, 0. And this one 0, 1. So like, just let me give you a more like concrete example for the sake of answering your question better. Example 4, right? So let's think about the vector A is something like, let's say minus 3, 4, okay? So that is minus 3 x hat plus 4 times y hat, actually, all right? And so if I plot, let me just plot here. X hat looks like this, let's say, all right? And y hat looks like that. They're vectors of length 1 that point respectively in the positive x and y directions. So to build the vector minus 3x hat plus 4y hat, what that means is I take 3 copies of x hat, but in the opposite direction. This minus makes me go in the opposite direction. So like, I would do 1, 2, 3. That's my minus 3x hat here, okay? And then I do 4 copies of y hat going vertically. 1, 2, 3, 4. So there's my 4y hat. All right? And so you see from taking minus 3x hat plus 4y hat, I obtain the vector minus 3, 4, which we can, I'll draw as a purple. thing right here, see that's specifically this vector. It was supposed to be straight, my bad. So there you go, there's A. Does that make sense?
Yeah.
Okay. So A sub x and A sub y, these are called the scalar components. So these two guys right here, scalar components of A. And these guys down here, this is the vector components. You know, these are both vector components of A. Vector components are vector, scalar components are scalar, right? You have to take the scalar times x hat plus the other scalar times y hat to get the vector that you're starting with. Yeah.
You might have already said this. So you said x hat and y hat, they would translate in some texts to I and j.
Oh, yeah. So, yes. So x hat is oftentimes I hat, or just something like that. I don't know. Yeah. All right, so the notations x hat and y hat are common in both physics, in higher level physics and engineering, all right? So I'm not just like making up a notation nobody else uses. I learned this notation in my physics major, all right? So, and it's a robust and useful notation that has a lot of generalizations, which are interesting. Okay, anyway, so that's just the basics. Now, how do you add vectors? All right, so if you've got two vectors, if we have a vector A plus vector B, the way they do that is like this. We add them tip to tail. So like A plus B is literally this right here, okay? That's how to do it geometrically. How do you do it algebraically? Like how do you like example 5. Suppose you've got A is, like 1, 3, and B is like 1 minus 3. How do you add those? What's A plus B?
You would add the x components and the y components together, or add the two x components together.
Yes, add the x components to the x components. We add the y components to the y components is what we do. So 1 plus 1 is 2, 3 minus 3 is 0. You get 2, 0. Now the picture for that is something like this. A is like this, and B is like that. So A plus B, you see the vertical part cancels out. What goes up goes down, and you're just left with a 2, 0 vector down here. That's the geometry of what's going on. So to add vectors, it's very simple. It's very simple if you already have the vector broken down into its so-called Cartesian components, right? Ax and ay are the Cartesian components. If you have a bunch of vectors and they're all in their Cartesian, if they're already broken down into Cartesian components, you can just add the x's to the x's, add the y's to the y's, and you get the total x and the total y for the resultant vector, right? This is how we add vectors, algebraically, geometrically. So we'll do a bunch of examples about that. I'm just getting us started on that. The other thing I should talk to you guys about is magnitude. What's the magnitude of a vector? I think I'm gonna put it here, if it's okay with you guys. I'll work myself into a corner at the end of class. It's a bad habit, but so what would the magnitude of the vector be? Right? Magnitude, or the length of A, we define to be A. It's equal to the square root of ax squared plus ay squared, since we're in 2 dimensions at the moment. The vector symbol matters. A without the vector is its magnitude. A with the vector is a vector. They're different, right? The magnitude is just a number. All right, so Let me point something out here. If, definition, if we take a constant times the vector, how's that go? I mean, I already did this, but let me do it again. So the way that works is we do c times the first thing, c times the second thing, all right? That's the definition of scalar multiplication. When we multiply a vector by a number, we multiply both the x component and the y component like that. Right? This is called scalar multiplication. The reason it's called scalar multiplication is it basically just rescales the vector, right? If I multiply by 2, for example, if I do 2 times, like, let's say 1, 2, I get 2, 4. And just like to plot that for a second here, here's 1, 2, and here's the other one. So like, if this is A, this is A, altogether we've got 2A. Right. Now, all right, so another thing I should define for us is unit vector. So a hat is equal to 1 over a times a. Now there's something I'm assuming here, and it's kind of an important thing. When is the magnitude of a vector 0? If it's what? If it's like the 0, 0 vector, then its length is 0. But otherwise, the length is non-zero, right? So when we're dividing by the length, it had better be non-zero, okay? But if it is non-zero, then this is a unit vector. Now the reason it's called a unit vector is it has length 1. And we can try that out here. Let's try it out on example 7 here. For example, if I have A is, let's say, 3, 4, what's the magnitude? 5, very good. So it's the square root of 9 plus 16, which, as you have told me, is 5. Square root of 25 is 5. So what's the unit vector? What's a hat? 1 over 5 times 3, 4. That's the unit vector in the direction of A. Okay? Let me draw this all together here. What does this show us? So if you look at that, we can rewrite this a little bit, and we can see that what we really have is that 3, 4, right, is equal to 5 times a hat, isn't it? What am I saying? I'm saying that the vector 3, 4 is 5, which is its magnitude, times the unit vector that points in its direction. This is part of a more general comment, which is like, generically speaking, we can write any 2-dimensional vector, in fact any 3-dimensional vector, as long as it's non-zero, as its magnitude times a unit vector which points in its direction. This is the equation which summarizes the statement, any vector can be written as a product of a magnitude times a direction. The direction is a unit vector. The magnitude is the length of the vector. Any vector which is non-zero can be written as a product of a magnitude and direction. Now, if we were doing units, like we're talking about a force vector or a velocity vector or an acceleration vector, then every component, all the scalar components of these vectors should have units, like meters or meters per second or meters per second squared, et cetera, et cetera. However, the unit vector will never have that. It's dimensionless because the unit vector is formed by dividing the vector by its magnitude, which have the same units. So the unit vector will always be dimensionless, which is nice. All right? So to recap, a vector in the plane we can understand by looking at its x and y components, and we can write any such vector as a product due to magnitude and direction. Now what's the other thing we can do for a vector in the plane? We can also describe it in terms of its, remember polar coordinates? Standard angle. We can describe the direction of a 2-dimensional vector in terms of like the counterclockwise angle swept from the positive x-axis. But we'll talk about that next time. All right, guys? So that's where we got to today. So. You stop it?